And thank you all for participating in what I think is going to be an exciting CEDAR workshop that we've structured as a tribute to the contributions of Colin Hines to our field over many years. I've tried to assemble here a group of talks that I think are at the cutting edge of gravity wave studies at present in honor of Colin's many contributions, and I hope we'll be able to have a nice discussion following each of these with Colin online. Before beginning, I want to say a few words about Colin's contributions to our field. When I began to study gravity waves as a graduate student with Marv Geller many years ago, I quickly learned that the field and the current understanding at that time had been contributed largely by one person and his various co-authors, and that guy is Colin Hines. Colin recognized gravity waves as the source of ionospheric disturbances that were seen for many years and that first revealed the presence of gravity waves at high altitudes, but he had to overcome stiff resistance to his ideas because, as he'll describe shortly, turbulence was sort of the prevailing view at that time. So his paper in 1960 was actually revolutionary. It defined the field for us. That paper, Internal Atmospheric Gravity Waves at Ionospheric Heights, remains the most highly cited of all gravity wave papers to date. And following that came a long series of additional studies by Colin and his colleagues exploring all kinds of additional applications. He looked, for example, at momentum transport and deposition. He explored instabilities, thermospheric heating, viscous damping, and the reflection and ducting of gravity waves that occur in complex environments. So, in a sense, his seminal initial paper and his successive papers laid the groundwork for studies of gravity waves that span the next 2 generations of researchers. So as a student, of course, I was eager to meet this inventor of our field, but he unfortunately began a 10-year hiatus just before that could happen. So I had to wait until 1984 to actually meet Colin at the Middle Atmosphere Symposium, at which he made his reacquaintance with our field, and that was in this room in this hotel at that time. So it's kind of coming full circle, I think. So thereafter, Colin and I became friends and colleagues. I had the opportunity to serve with him on the Arecibo Science Advisory Committee when he was the director there. He was a gracious host for me when I happened to go to Toronto as an external examiner for one of Dick Peltier's PhD students. And each time we met, at meetings or otherwise, we would discuss and debate data analyses, different people's attitudes about things, various theories, and especially gravity wave saturation processes that were near and dear to both of us, and about which, of course, we never agreed. But we did agree generally that most everyone else was almost certainly wrong. So it's been a privilege and an honor to count Colin among my friends and colleagues for almost 30 years now. And we are all privileged, I think, today that he has agreed to participate with us in this workshop as a tribute to him. So let me turn now to our workshop presentations. We'll begin. Oh, sorry about that. It's my screensaver. That's Colin in that picture, and you can tell that he's probably the lion. So let me turn to our workshop talks. There is a list of them here. Colin is going to lead off, starting steps on my path to internal atmospheric gravity waves. I'm going to follow on with a discussion of numerical studies that specifically address the debates that he and I have had over many years. We're going to hear from Albert Herzog about observations of gravity wave momentum fluxes and intermittency with very high resolution, constant pressure balloons that give you an intrinsic perspective on the gravity wave spectrum very nicely. Brian is going to talk about more recent studies of self-acceleration effects. Sharon Vadas is going to present a talk by Nichols et al. On gravity waves at very high altitudes seen in the ionosphere. Joe Hube is going to talk about applications of neutral gravity waves in the seeding of equatorial spread F. And then Mike Taylor is going to talk about an exciting new technology that I think will also help us quantify gravity waves more in greater detail in the future with some specific applications that he's made recently. So Colin, I'm now going to switch, with any luck at all, to your presentation.
I want to begin these reminiscences with an act of faith. Faith that Dave would have said mainly nice things about me in his introduction, which as I write, I have not yet heard. So, thank you, Dave, for your kind introduction, whatever it was. And thank you too, and your colleagues, for conceiving and implementing this workshop session as a tribute to me. I feel greatly honored. Thanks also to my own offspring, David Hines and Karen Hines, for their part in arranging and bringing off my end of this teleconferencing session, which, I am told, puts me in the same league as Bill Gates, if only. Finally, my thanks go to the NSF and its CEDAR program for supporting the idea of the session and its consummation today. They have been generous in this as in their earlier support of me and my group at the Arecibo Observatory. My remarks today will be essentially a précis of those I made many years ago at an after-dinner event in Adelaide, Australia, which have since been published in Volume 130 of Pure and Applied Geophysics, 1989, if anyone cares to get more detail. My work on gravity waves began in 1954 in Cambridge, England, where I was a doctoral candidate. Since many or most of you in the audience were not even born at that time, I cannot ask you to remember what the world was like then. Instead, I must reconstruct it for you. Firstly, the world was devoid of cell phones. As a consequence, students had time to actually think about their research work. That process was abetted by the simultaneous absence of any high-speed computers to speak of, which they might otherwise have hoped would do their thinking for them en route to thesis material. The world at the time embraced no artificial satellites to facilitate long-distance radio communications, so such communications were conducted either by reflection of HF waves from the ionosphere, preferably with it in an undisturbed state, or else by over-the-horizon scattering of VHF waves from whatever small-scale irregularities in the refractive index might exist, generated by who knew what. The most popular candidate as the generating mechanism, and so as a topic of research interest, was atmospheric turbulence, a field whose theory was just then being opened up by George Batchelor and colleagues, also in Cambridge. Independently, however, medium frequency and high frequency observations of the ionosphere were revealing irregularities at much larger scales, and these often exhibited horizontal progression, cautiously termed drift, in the absence of any established mechanism of motion, though it was widely hoped that they represented winds. The largest of all these irregularities, both in scale and in intensity, were traveling ionospheric disturbances, or TIDs, which exhibited also a vertical progression invariably downward. This downward characteristic led many to think that the TIDs might be generated at higher elevations, perhaps at what we now call the magnetopause, by interaction with what we now call the solar wind. If so, the downward progression might be accomplished by magnetohydrodynamic or hydromagnetic waves, that is, alpha-ing waves, which had been introduced to science only a few years earlier. I had already worked on such waves in Ottawa before going to Cambridge, so I was asked by Jack Ratcliffe, the chief guru of ionospheric studies at the time, both in Cambridge and internationally, to look into that possibility. I began by viewing the observations, always a safe start for a theorist, as they had been reported by Monroe from Australia. He in turn referred to fellow Aussie David Martin, who had invoked some form of atmospheric wave as the causative agency, but who went on to propose an unsatisfactory geomagnetic interaction to account for the downward progression of the TIDs. His story included the effects of gravity, which I had ignored in all my previous studies, so I was prompted to include them to see if they seriously changed any of my earlier conclusions. To my surprise, they opened up a whole new class of waves to me, internal gravity waves, of course, and suddenly all the unrelated observations that were cluttering up my memory fell into place within a single scheme. The downward progression, for example, was to be expected of gravity waves generated in the energy-rich troposphere, and so forth. Some time and much argument was required before this scheme was accepted widely, but I trust you in this audience will agree that at last it has been, or you would not be involved in seeking out its still hidden treasures and in extending it, as I believe you are doing. I'm looking forward to learning just how as this workshop continues. So many observations fell neatly into place, instantly and in an ongoing expansion, that challenging new observations, sufficient to spur the demand for and production of new theory, were in meager supply for a time. I found myself to be constrained to building new theory on old theory. This struck me as a bit incestuous and therefore dangerous, so I quit the field for a period of rehab and exploring the magnetospheric convection. When at last I returned to gravity waves, I found to my delight that a new observational feature had come to center stage and was yet unexplained, the so-called M⁻³ spectral tail. Jerry Weinstock was the first to identify it as resulting from nonlinear interaction, but the complicated mathematical formulation that he called upon to support his view was difficult to follow or agree with for many, including me. This resulted in several half-starts at alternative explanations by several individuals. Also, it resulted in frustration of the type encountered by the legendary 10 blind men trying to describe an elephant, with each holding on to a different part of the beast. Dave Fritz recorded the situation by means of a notorious view graph, which I trust he will now display for me and for you. When I, in turn, produced my own theory of the M⁻³ tail, using nonlinear consequences of the Doppler term of the Eulerian equations, evaluated ultimately via transformation from the linearized Lagrangian equations, Dave was kind enough to lend me his view graph. I copied it and then added to it a new onlooker, myself unblindfolded, able to see the elephant in all its glory. I trust he has the edited view graph on hand and the decency to show it now. Well, that's the way I left the field upon my retirement in 1992. I have not read a word about it since then. This leaves me poorly placed to hazard the traditional onward and upward forecast as to the most promising paths of future research. I can only mention the areas about which I was most curious when I was last in contact with the field 2 decades ago. First was the question of parameterization for purposes of large-scale circulation studies. Would my own survive or be supplanted by one of better design? And if supplanted, with what improvements of design and consequences? What tales would these parameterizations have to tell about the role of gravity waves in altering the circulation? What was the most appropriate input spectrum of gravity waves for any parameterization? What, indeed, were the most important sources of gravity waves, of the general background spectrum, and of individual events? No doubt some of these questions have been answered by now, and the forefront has moved on. beyond my sight. But I am here to learn, not to predict. I look forward to seeing the rest of this workshop, and in advance I wish to thank all participants in it for their participation and for bringing me up to date. Thank you all.
Okay, let's open it up for questions for Colin, if there are any. Brian?
Is that he referenced the elephant plots?
They're coming.
Okay.
Other questions for Colin? I have a question, Colin.
Yes, sir.
Given our long debate over gravity wave saturation processes, and given the potential now to do very high resolution DNS, which I'm going to show an example of shortly, and the ability to construct from that both Lagrangian and Eulerian spectra, what do you imagine might happen when we do that?
Well, I think that you will produce substantiation of the theory produced, transforming from Lagrangian to Eulerian coordinates, and the consequent saturation in Eulerian.
And given that these simulations would necessarily be constrained to a somewhat idealized and discrete flows, in a limited computational domain, are there warnings that you might offer in terms of continuous versus discrete wave interactions that fit your theory?
No, I think you're better able to answer that question than I am, Dave. I'd like to see a spectrum, an input spectrum that has a gap at high wave numbers where the tail is expected, to see whether that gap persists or not. In the Lagrangian transformation theory, that gap would be closed in by nonlinear processes.
Well, I hope that we'll stay in contact on this. We're very eager to progress. I think the simulation I'm going to talk about shortly will not answer all of your questions. Sharon, you have a question?
Hello.
Hello?
This is Sharon Vadas, and I wanted to say thank you for doing this presentation, and I'm a big fan of all of your papers. I've never met you, but I've read a lot of them. Wanted to mention one of the things I'm working on now is body forces in the thermosphere, and you wrote the original paper on that in the 60s or 70s, I forget when. And anyway, my question is I know you haven't been in this field for 2 decades, but if you were to predict what the biggest sources of gravity waves were in the thermosphere, what would you just guess, just based on what you think?
I still think the biggest sources would be lower down in the atmosphere, just because there's so much energy down there. I would like to add to the comments that were recorded earlier that one of the things I was curious about as I left the field was concerned the effects of horizontal wind shear in the jet stream. I know there have been many studies of vertical jet stream shear with waves radiating off to the upside and possibly downside. But at the shears in the horizontal on the flanks of the jet stream, there are destabilizing effects of turbulence or of simply moving parcels of air around, but no stabilizing effect of gravity to counteract them. So I suspect that the flanks of the jet stream might provide a powerful source for worldwide gravity waves.
Thank you.
Any other questions?
Sure.
Yeah, Erdal.
Good morning. My name is Erdal Eid. I'm a young scientist working with gravity wave parameterizations and how they propagate into the thermosphere from their meteorological sources. So I was wondering, when you started working with gravity wave theories and their possible or probable effects in the ionosphere, and what did you expect from the aeronomy community, how their reactions would be if one would suggest gravity waves can probably affect the ionosphere? Did you have any discussions in the past? Did you have any experience arguing with people? Because upper atmospheric people, still most of them do not want to accept that small-scale features coming from below can affect the upper atmosphere, meaning the ionosphere-thermosphere.
Well, thank you for that information. I'm surprised to hear it. There seems to be so much evidence to the contrary that I would have thought they would have come around by now. Is just the smallness of scale that you're speaking of, is that why they're remaining barbarians?
Any comments there at all?
I had better not make a comment because I'm still new in the field, and maybe in the future.
You can probably learn from Colin's edits of the elephants. So. Anything else?